welcome everybody. My name is Susanne-Rentsch-Smith and I'm working as a geophysicist in our Shearwater Technology and Innovation Center in Norway. I've been working on multi-component streamer processing techniques and streamer design for almost 14 years now. And today I would like to present some answers to what are the key design elements of a multi-component streamer. And I shall do this with some theory and practice. But before we dive into the details, I would like to open with some learnings from the EAGE Marine Acquisition Workshop that was held a few months ago in Oslo. Erling Wagnes, the chief geophysicist for exploration in Equinor, said that seismic is a truly amazing technology and one of the most advanced measuring technologies available to mankind. And this clearly celebrates the technology achievements in the industry over the last decades. However, from the workshop, it also became clear that the market wants to lower the exploration costs, not just from fewer dry wells, but actually lowering the cost of running seismic exploration, while also graving for a precise definition of ever smaller targets and for the increased recoveries. Your smaller targets require a better probability, and for that, better seismic is key. And on the other hand, the procurement process is driven by specifications and costs, and there is no such thing as an assessment of better seismic in the process. And typically something that is better in quality is not cheaper. So in order to solve the quest of an increased economical efficiency while maintaining or even improving seismic quality, we do require a full feedback loop for innovation. We in Shearwater, as you know, are clearly committed to geophysics. We innovate collaboratively by integrating our 4 units in technology, operations, software, and processing and imaging. And only this full integration enables us to have a continuous development loop, which is instrumental in solving the industry's challenges of today, but also the ones of the future. However, we also recognize that we cannot do this unless we collaborate closely with our clients, and that this collaboration needs to be transparent and mutually beneficial. That also applies to designing a multi-component streamer, which is an engineering balancing act. On one side, one has the key requirements and constraints. It needs to be fit for market demand. It needs to be fit for geophysical purposes. It needs to be operationally viable and have a good economical production cost and also maintain an economical cost of ownership. On the other side, you have the key design elements, which are your output spacing, your sensors, your sensor mounting, your skin, your fillers, the number of sensors you may use, and whether you go for single sensor or analog groups. For instance, your output spacing needs to be fit for the geophysical purpose, but a dense output spacing may drive the number of sensors up, which in turn affects your production cost. So it all links into each other. Let's start with looking at the output spacing. When I say output spacing, I mean the spacing of the delivered field data, which are typically either noise attenuated data or group formed data. The system should enable 3D deghosted data for the entire seismic bandwidth, which typically ranges from 1.5 to 200 Hertz. A P-only deghosting is perfectly acceptable up to, say, 25 Hertz, but above 25 Hertz, it is expected that you use the multi-components. Otherwise, what's the point in a multi-component streamer? When you look at the output spacing, you need to ask yourself the question, is signal aliasing acceptable? We have today commercial systems that deliver 12.5 meters, 6.25 meters, and 3.125 meters output spacing. I'm showing here a snapshot taken from Askedom et al. It was in their expanded abstracts of the 2016 EAGE conference. And you see an FK spectrum here of a P upgoing wave field sampled at 12.5 meters. And as expected by theory, after 60 Hertz, you hit your Nyquist wave number and then your signal wraps around and it comes back, crossing the zero wave number at about 120 Hertz. This is perfectly accepted at a 12.5 meter output spacing. So the remaining question then is there a desire for anti-aliasing protection, or do we prefer the ability to de-alias in processing, or in other words, should this energy here be removed, or is this energy desired to be left in even though it is aliased? When we are talking to customers, they do appreciate this energy, so they actually want to keep it in, whether it's being aliased or not. Customers also appreciate a denser spacing than 12.5 meters, but not extra cost this may entail. And with that, we would conclude that the system providing 3.1 to 5 meter output spacing is actually gold plating, with little return on investment, and 6.25 meters or 12.5 meter spacing is absolutely sufficient for today's market. Now let's move on to the choices of sensors, starting with the hydrophone. Now, hydrophones have been in the industry for several decades, and they are actually well understood, and overall it's not that complex anymore. One has to ensure the PIC satisfies a good operating depth range, typically between, say, 4 and 50 meters. You also want a good operating temperature range, so you're not as restricted at where you can tow. You want suitable sensitivity to measure fine changes in low amplitude reflections, thinking 4D here. And the hydrophone also needs to handle requirements for the dynamic range that come from challenging acquisition methods. Like, for instance, here I show a snapshot of an acquisition method from Lee et al. That they showed in the Marine Acquisition Workshop in 2018, where the sources are put on top of the spread, and with that you reach some very near offsets, and possibly those near offsets receive some very high amplitudes. And in order to mitigate that you may exceed your dynamic range, you may want to consider choices for gain settings. When it comes to particle motion, velocity or acceleration, there are several options, with the two most obvious choices being geophones or MEMS. Both are valid options, of course, because there are systems out there today that have either. If one was to go for geophones, one needs to take into account that they may require either being gimbaled or require complementary orientation measurements. And if one opts for a gimbaled version, that may increase the sensor size, which may have a knock-on effect on the streamer diameter and consequently drag. We clearly prefer MEMS because they are low in cost and they have a very low power consumption. They are miniature in size and light in weight, which is good for buoyancy as well as signal fidelity. By accurately measuring down to DC, one can actually obtain a very accurate sensor orientation. For instance, in our isometrics platform, the accuracy is better than 0.1 degrees today. Small rotation errors, we have learned, can lead to increased noise, in particular on the horizontal components. And last but not least, MEMS benefit from a very low distortion and a nicely flat frequency response from DC to several kilohertz. And for more information, you should look at the publication from Paulson et al., which was in their EAGE abstract from 2015. When it comes to sensor mounting, one has several options too. The options depend on the filler or the platform type. Shown here in the pictures are two platform types. Gel-filled platforms typically consist of a stress member, which are feeding through spaces that are enclosed by a skin. The sensors are mounted within the spaces and usually in the cable center. On the other hand, we have a solid platform here. And there the cable core, stress members and electronics typically sit in the center, and the sensors are off-center. In both scenarios, the sensor mounting has to ensure the sensors stay indeed where they intended to be, that they pass extensive reeling, that they prevent the sensor from being crushed. Ideally, we also want to see some dampening of the dominant noise mode without compromising the signal, and prevent or minimize coupling into other noise modes. Next, to consider are streamer skins. Their primary purpose is to enclose and protect the sensors, fillers, electronics, and stress members. You have to make a choice about the skin's stiffness. But it's a trade-off. Soft skins are easier for handling, like moving, reeling, or storing. But on the other hand, stiffer skin is better to mitigate the turbulent flow being recorded by the sensors. So it improves your raw sensor noise levels. The thickness of the skin also affects the effective stiffness. It also affects your reliability, things skin cuts or punctures, but if you choose it too thick, it can also affect your signal. The choice of your skin may also affect the weight and with that the buoyancy. And last but not least, you should also think about the anti-biofouling properties in your skin, because when barnacles grow slower, it would reduce the impact on HSE exposure, and less cleaning cycles are also positively impacting the total cost of ownership. Before we can look at the last three elements, the filler, the number of sensors, and the single sensor versus group assessment, we need to have a quick detour to understand the noise modes at play. When a streamer is towed under tension through the water, the following noise modes are excited. You have the inline vibration noise, which, as the name suggests, propagates inline. We have the torsional vibration noise or angular vibration noise, which twists and rotates the streamer. It does not just add noise, but also constantly changes the sensor's orientation, and its effect increases the further the sensor is away from the cable center. Next, we have the transverse vibration noise, which ripples through the streamer and is by far the most dominant noise mode on the particle motion sensors. And finally, here at the bottom, we have the local flow noise that is mainly sensed by the hydrophones, but the local flow is, of course, the root cause of all the noise modes that are shown above. Let's focus on the transverse vibration noise, as this is the most dominant noise mode. Teigen et al. Showed at the 2012 EAGE that it can be approximated with a model of a slender uniform beam that is subject to axial tension and a certain bending stiffness. In the two plots below, you see the frequency, wave number relationship, and the colors represent the different stiffnesses. The green color being the most solid, and the blue color being the least stiffest. On the left-hand side of the plot, this one is for the low tension case of around 300 kilos, and that you typically observe at the tail of a streamer. Here you can see how the effective bending stiffness significantly changes the frequency wave number dispersion relationship. On the right-hand side, you can see the same curves, but now calculated for the 2000 kilo tension, which can be found near the front of, for instance, an 8 kilometer streamer. And now the curves are much closer together. And comparing the left and right-hand side, we can also see that the stiff, solid streamer types very little is tension, while the ones with smaller bending stiffness have an increased wave number range one needs to cover when considering sampling this noise or designing a suitable group. The theory can predict the dispersion characteristics of the transverse vibration noise, but it gives unfortunately no information about the amplitude, the bandwidth, dampening, and the coherency lengths. And in order to validate the theoretical curves from the previous slide and answer the questions on the amplitude, bandwidth, dampening, and coherency lengths of the noise, we built fully sampled streamer sections with identical sensors and electronics, but we varied the mechanical properties of spacers, fillers, and skins. We towed them in a controlled environment in a fjord in Norway within the same streamer, and filled what we call an evaluation landscape, covering a large number of operational conditions to study the noise in detail. So the landscape consists obviously of our mechanical properties. Then we have here an axis that mimics the tension along the cable, and we increase tension by adding C anchors to our streamer. And then we also sample different towing and environmental conditions by, for instance, changing the towing directions, the tow speed. We swap the sections around along the streamer. We change the tow depths. We apply steering. We record in turns, and we also check in different weather conditions. So what you see here is actually FK spectra from the evaluation landscape, sampling tow speed at 4 knots, 5 knots, and 6 knots. On the horizontal axis, you have different panels. So you have some stiff streamers at the very outside. Then you have here a family of streamer sections of a highly dampening, low stiffness gel. And here you have a hard gel with less dampening properties. You can also appreciate that the change in tow speed changed the tension, and that the tension change changed the frequency wave number dispersion relationship. So if you compare this and this, you can clearly see how the curves changed around. Now let's focus evaluating this a bit more closely. And for this, we take one example from each type. So we have the solid streamer, we have a hard gel, and we have a gel with a highly dampening function here. We have a low tension case of 300 kilos, mimicking the tail of the streamer, and we have a high tension case here, mimicking the front end of a streamer. We overlay the theoretical curves we have seen before, and we actually get a pretty good match. One exception is the high tension, low bending stiffness case, where we start to observe some inverse dispersion above 20 Hertz. One can further observe that the noise in the solid streamer is well shaped, being very sharp and concise in the FK, while the noise in the gels appears more, I guess fuzzy is the right word. This shows that the coherency length of the noise in a solid streamer is larger across the frequency range than in a gel-filled streamer. We also plot here the medium power spectral density curves for each case, and can now observe at which point those diminish below a certain threshold, which we believe noise attenuation may no longer be essential and the data could be used as they are. And we clearly see that the solid sections start off with lower noise at the low frequencies, but then they decay much slower with frequency than the gel-filled streamers. As for the gel-filled streamers, it is also quite clear that the noise in the harder gels decays slower than the noise in the softer ones. And now this has implications on the sampling requirements. To explain this, let's go back to the simplified theoretical plots. It's less convoluted. The smallest wave number to cover is dictated by the high tension scenario. The 3 section types do not differ much, and if we assume we only intend to use the measurements, say from 20 Hertz onwards, we can estimate the smallest wave number to be in the order of 0.3 per meter. In contrast, the highest wave number to sample depends on the low tension scenario and the maximum frequency you need to attenuate the noise in. Because the 3 streamer types required noise attenuation over a different range, we project each maximum wave number from that frequency. Now, here comes an interesting observation. The lowest maximum wave number comes as expected from the solid streamer, but if we go then down in stiffness, we can see that the streamer with the higher dampening properties actually has a lower maximum wave number, and the highest wave number we observe is from the stiff gel family at about 2.2 per meter. So now let's take this learning and look at some consequences for the single sensor versus group analysis. Let's build a group and start off with, say, 5 sensors. We have learned the highest wave number to cover was dictated by the low tension, and a wave number of 2.2 per meter requires in the order of 45 centimeters sensor base spacing in our group. The smallest wave number to cover was 0.3 per meter, so we need to see how fast we have a suitable group response at about 0.3 per meter. In this plot, we can see the group's response, the horizontal axis being wave number and the filter response being on the vertical axis. You can see the Nyquist is hit at 2.2 because this is how we put our sensor spacing. And then the number of sensors in your group actually dictate how fast you get to the first notch, or how fast your filter response increases to a high frequency response or a high response. And we can see here at 0.3 we get a less than 10 dB noise attenuation, so that's not good enough. So let's add some more sensors. 7. So now we have 7 in a group. Well, that looks better at 0.3. So now we are at about 15, maybe 20 dB noise attenuation. But this second lobe is not really desired. So let's add another 9 sensors. That looks okay, but it's still not great. Let's be generous. Let's try 11 sensors. That's not too bad now. But is it actually good enough? And for that, I'm going to take the response of the 11 now, which you see here. It's the same filter response as before, but just picking the curve of the 11. And now what you can do is when you look at the two dispersions from the different tension scenarios, you can project the wave number response onto the dispersion curves to get the response as a function of frequency. And this is what you see here. As you can see in the low tension case, you get to about 20 decibel noise attenuation power. However, as we have seen earlier when looking at the amplitude behavior from the field test data, you need in the order of 35 decibel, around 25-30 hertz in order to make that signal useful. Now this is where single sensors actually come in handy, because with single sensors you can tailor your group response to your need. Here you see a very simple digital filter optimizing the response for a group of 11. It's exactly the same group as for the analog, but now we digitally enhance the filter response. We now achieve the 35 decibels, but we need to sacrifice a little on the zero wave numbers as well as on how it decays from the Nyquist wave number. The projection of this response onto the frequency axis for both the low and high tension scenario looks pretty appealing now too, doesn't it? In fact, you don't have to stop here at all. Having access to single sensor data, you can actually tailor your response not just along the streamer accounting for your tension needs. No, you can actually tailor your response to create a wave number notch for each frequency, optimizing your noise attenuation power everywhere and putting your notch exactly where you need it. So even if you use a group sensor layout, single sensor data from this group will allow you to do more and adapt better to the noise or the noise conditions you encounter. So our take on single sensors versus groups is that, yeah, you can do analog groups, but they are static. They need to fit along an entire tension range from the tail of your streamer to the very front end. At the front end can be a 3 kilometer streamer, an 8 kilometer streamer, or maybe even 14 kilometer streamer. which is a pretty hard ask for an analog group, and you will need to compromise on that. In contrast, the single sensor data access enables you with a lot of flexibility. You can adapt to the noise attenuation needs you encounter. You can even go as far as designing frequency-dependent K filters, putting a notch exactly where you would want it. Furthermore, you can change the number of sensors you want to use. Like in the high frequencies, you might want to use less sensors than what is in your group, and in the low frequencies, you might want to borrow sensors from neighboring groups to enhance your noise attenuation power. And furthermore, in single sensor access, you can counteract or repair data flaws. Like if a member of your group dropped out, died, or you have a spike in your data, you can basically counteract that before it leaks into your filter response. The single sensor option is also future-proof. It allows you for continuous improvement in processing without actually having the costly need to change out your streamers or your hardware, which in the current condition is a very desirable feature to have. And with that, it is actually time to conclude and summarize what we have learned. I hope I have demonstrated to you that we have a very solid engineering approach for streamer design. We have walked through the key elements for designing a streamer. We've talked about the output spacing, and that 6.25 or 12.5 meters are sufficient, and one doesn't need to gold plate a system with a 3.125 meter output. We also have learned that we actually prefer the MEMS for our multi-component sensors, as they give us a higher flexibility. The sensor mounting depends on the filler, so we have well understood this problem. We have also shown that the choices of skin affect the handling, but also the noise performance and reliability, and you have to do a trade-off there. And I hope I have also demonstrated that the choice of the filler is important, and that solid fillers have very little dampening of the vibration noise, but on the other hand also have a reduced wave number range, and with that have a lower sampling requirement. Gels, on the other hand, have a higher vibration noise dampening, but increase the wave number range you need to cover, so you need to be very aware of your sampling requirements. And last but not least, we believe single sensor trumps analog groups, because it gives you additional flexibility and allows you to adapt to your conditions that you encounter, and it also future-proofs your hardware design. And with that, I would like to thank our manufacturing teams, technical support teams, and the crew from our vessels and the test station, as well as our processing and imaging teams for all their contributions. And of course, I want to thank you for joining my presentation. I think the floor shall shortly be open for questioning.